Up next is Stig Telfer. Mr. Telfer has a background in R&D working for various prominent technology companies, particularly in HPC and software-defined networking. Mr. Telfer is now CTO for StackHPC, a consultancy specializing in the convergence of cloud, HPC, and big data. Mr. Telfer is also co-chair of the OpenStack Scientific Working Group, a globally distributed grouping of research institutions using OpenStack for research computing use cases. Today, Mr. Telfer will present on cloud middleware technologies. Thank you for joining us today. Mr. Telfer, you may begin.
Thank you. Thank you very much. I hope you can hear me. So, cloud middleware technologies. I guess actually we should clarify this as being very much focused on the open infrastructure side of this technology, particularly because you wouldn't really see much of the middleware or the lower ends of it in the public cloud world. I think that's a closely guarded secret. So what I'm going to talk about today is some very implementation focused exercises in cloud middleware and how they've been applied to HPC infrastructure. But first of all, I guess unless you work in the space that we work in, which is a fairly rarefied niche, I should probably introduce the company because I'm standing among some very luminary people in the schedule today, and we are just a small firm based in Bristol. So the company's been going almost 5 years now. So we started first week of January 2016. And we're a small company in this niche market of open infrastructure and applying it to high-performance computing use cases in particular. We do a lot with open infrastructure. We do a lot with OpenStack in particular. And really, I'd say that the company's purpose is divided into these four specific things. So we work with upstream OpenStack, the source code and the community to develop and advocate for this capability and the requirements needed for research computing use cases in particular. Secondly, we also work with how to develop and bring HPC-like technologies into a cloud-like context. So actually, it's been very fascinating to hear references in passing in a lot of the previous talks today into how technologies like RDMA network fabrics and HPC-enabled storage can be brought into a cloud context and used to good effect. Thirdly, we assist with institutions and other organizations in helping them to integrate or migrate to more sort of cloud-oriented research computing infrastructure, how to bring that in alongside HPC environments in a complementary way, or indeed to run HPC environments from within a cloud-native control plane. And finally, I guess the fourth piece is really about the social infrastructure of what we do. Scientific OpenStack is about how do we work together as an open infrastructure community, bringing people together, sharing ideas, exchanging know-how. That kind of thing. So that's our company in a nutshell. I guess the next question on people's minds might be, well, that's who, but what about the why? And I suppose everyone knows about cloud, and we hear about how fast it is developing and changing. And I think that a lot of innovation is happening in this cloud infrastructure space, particularly around the three areas of flexibility, automation, and failure, or rather the management of failure. And I think all three of these are going to be completely relevant in growing HPC infrastructure to ever bigger scales. So how do we harness those things, and how do we make use of them? So HPC infrastructure teams at research institutions that do harness the innovation of cloud infrastructure gain benefits from these things, from flexibility, automation, and scale. And that's visible not least in the class or the breadth of service that a team of finite size can provide to the users that they serve. So I guess that the way that we see things as they stand today is what we internally we call HPC Stack 1. And the idea here is that a research computing infrastructure, a service rather, will be providing different services upon different infrastructures in a way that is somewhat structured into silos. So the ultimate motivation, I guess, that these teams have is how do they keep up with changes in an evolving HPC landscape? And it's quite difficult when we've bought the hardware for our HPC system, for our big data environment, or for our AI or deep learning environment, and essentially they are being managed as discrete, separate software stacks. I think Deco is describing a very similar problem of how to manage that from within a Slurm context. So we take a similar approach to how do we pool these resources. How do we break down the barriers of these the structure between the different silos of hardware? And also we have this other interesting problem, which is that if we have specific hardware for AI, for example, the way that these services are managed and presented to users today typically means that the users are forced, or not forced, but they are required to sign up to operating or to working in those platforms using the software stacks that have been deployed on their behalf by the research computing services organizations that serve them. And in a system that is innovating quickly, that is not ideal. And there may well be competing software stacks or competing ways of doing things, other approaches, which essentially would be to some degree shut out based on the decisions made at deployment time or even at procurement time by the services that they work with. So the idea then is that we evolve this into something which is a little bit more fluid, a little bit more software defined, and we break down that structure. And then we pool our resources in terms of a large resource of bare metal, which may well be heterogeneous. We may well have hardware that is dedicated or well suited or well balanced for particular workloads and other hardware for other workloads. But if we bring it together as a heterogeneous pool, using the new developments in cloud middleware, we can present those using these software-defined APIs and provide services which are very much more loosely coupled and cut according to the requirements of the users and their specifications. So this comes down in three ways. We pull together all the hardware, and therefore we have this larger heterogeneous resource. We offer upon it a number of platforms which can pick and choose essentially the server equipment that they are making use of. And then we offer up to the science communities through conduits like RSEs and other similar groups, data scientists and so on. We provide to them these platforms which essentially become interchangeable Lego bricks. And the idea there is that different communities can innovate together. They can make use of each other's work in a way which is sharing of a platform, but entirely specialized to the domain of that use case as well. So we get this reinforcing cycle of innovation and invention coming on through the scientific communities that sign up to a software-defined kind of cloud-native approach to the way that they manage and consume their infrastructure. I think one of the early projects that we did, which was a big step in this direction, was the SKA Science Data Processors Performance Prototyping Platform at Cambridge University, also known as P-Cubed or Alaska. And so this system came into service, I believe, in early 2017. And really the idea of this system was to provide a level playing field. So we provide a pool of hardware, which is inherently quite heterogeneous. There is a batch of conventional compute resource, but also other interesting technologies that the scientists developing the software middleware for the SKA platforms for the science data processor wanted to explore and wanted to try applying different approaches to managing them within a software context. So the real purpose of the project in some ways was to provide this level playing field, and using OpenStack and software-defined infrastructure, we were also able to lay onto, to keep the analogy going, a nice clubhouse next to it, in which we were able to help the scientists to define these platforms using these kind of cloud middleware approaches. And so the software is, the machine is still in operation and is still delivering useful and interesting results for the science data processor community. But it does fundamentally remain a prototyping environment. So moving on from there, we can talk about a little piece of work that we've been doing also at Cambridge University with the Tier 2 system that Simon McIntosh-Smith was introducing, which is CSD3, the Cambridge Service for Data-Driven Discovery. So this machine has also been in production for some time. It is also inherently heterogeneous. It's not deployed using OpenStack. It's deployed in a far more conventional way, and it provides a single Slurm cluster as its primary workload. But as you can see, it is a heterogeneous system, so there's already considerable diversity within the service that it provides, and it is also this production facility at Cambridge University. So recently there was a hardware extension to CSD3 to extend its power, and the new project known as Arcus is a new tranche of compute nodes, which brings in two high-speed network fabrics and Mellanox InfiniBand and also Mellanox Ethernet, managed using the Cumulus Switch OS. So the switches become essentially top-of-rack servers with a whole lot of network ports within them. So bringing Arcus into the CSD3 environment was an opportunity to explore how we can evolve the HPC infrastructure management that the team at Cambridge University had developed and honed and improved over the years, and how we could bring in some cloud capabilities into it. Now, I suppose with a lot of things, a lot of people, when we think about cloud, we think about virtualization, but that's very much not the case here. We are actually doing physicalization of software-defined infrastructure. So it's presented as bare metal machines, but talked about in the abstract terms of virtual infrastructure. So instances, which we would normally think of as virtual machines, are, in this case, bare metal server nodes. And when we spin up an instance, the fans will be spinning up literally on a bare metal compute server. So once we step back a little bit and we've taken in that OpenStack environments can actually create physical HPC capable networked with InfiniBand or with other high performance network fabrics, can create this kind of environment. We see that actually using the abstractions of virtual infrastructure, of cloud, we can actually describe a physical and very capable HPC system as well. And at the same time, we get all of the performance. So we don't lose any performance because the machine that is created is essentially a bare metal machine upon which there is no software overhead incurred by the cloud layer. The trade-off for this is that we only get most of the flexibility of cloud. There are some bits that we obviously don't get: live migration, shelving, resizing, all of the bits that involve taking a VM and salting it away on disk and then bringing it back up somewhere else. Those bits we cannot do. But when we can talk about attaching network ports or deploying software images, injecting user keys, a lot of the work that we can do in terms of software-defined infrastructure is still available to us. And there's a few tricks in the bag as well, because the other pieces we can do with a bare metal OpenStack environment is that we have complete control, not only just of the middleware, but also of what you might call the topware and the bottomware of the system. We can talk to the BMCs and the BIOSes on these environments. We can talk to the network switches, so we can create an entirely customized system, customized to within the limits of general purpose hardware. So we can reprogram the BIOSes on the servers, and we can reprogram the RAID controllers in order to create a machine which is, to the best extent we can do, configured and specialized to the purposes of the software workload that it is about to be running. So perhaps we're running a Hadoop environment, in which case we would take all the disks out of RAID and present them as individual JBODs. Perhaps we're running a Slurm environment where we're looking for maximum sequential speed, in which case we will disable hyperthreading and maximize for low interrupt latency or highest core performance. To these extents, we can specialize the machine from a general class resource. So there's a lot of automation at the low level where we can use cloud infrastructure techniques to bring a complex and large-scale machine together. Arcus is 672 nodes and is deployed in a way in which, to the greatest extent possible, the drudgery of server bring-up is automated. In this case, once the servers are racked and stacked, someone is walking around and scanning the barcodes on the back of the servers in a sequence, and this then, through an automated workflow, builds up an inventory within the OpenStack environment, which is then able to process the barcode data, extract the information from them, and essentially build up the inspected machine state as to which network ports it is connected to, its place in the fabric, and the inventory of its processors, disk and RAM and other pieces. It's not a completely smooth ballet of technology at this stage. I think with every large and complex deployment, we also have to cater for the occasional spanner that low-level firmware will throw at us. And in this case, for example, we had to do all the early provisioning on the gigabit Ethernet because the ConnectX-6, the Mellanox NIC, boots up assuming it's connected to 2 InfiniBand ports. And so we had to then reprogram it to talk Ethernet on one of the other ports and then restart the process again through the 50 gig Ethernet instead. So this is a process. It's not a sort of a guaranteed this will work everywhere process, but it is a process which can be extended or customized in particular workflows to meet the requirements of particular infrastructure. Moving up the software stack, we're also able to use this cloud, the sort of the middleware automation in order to build the primary workload upon the system in a much more cloud-native middleware kind of way. And the approach that was taken here, we're quite pleased with, we're quite proud of, because it was very much born out of a close collaboration between the operational expertise of the Cambridge HPCS team and the OpenStack and cloud native expertise from StackHPC in order to build a Slurm cluster which is deployed using cloud tools such as Terraform or Ansible to describe the resources of the cluster, but at the same time to make something which isn't just essentially a little snow globe environment where the infrastructure is not really designed to be operated. This machine was very much designed to be operated in a way where it can be patched very quickly. It can be rebuilt. The software image can be replaced in a rolling sequence of upgrades, coordinating between the Slurm queues and the OpenStack infrastructure that underpins it in a way that brings about a easy to maintain and effective to maintain system without actually introducing large disruption to the users upon the system as well. And this is this is the process that is being rolled out today for the Slurm queues on Arcus. In terms of managing an OpenStack system with the 672 servers in it, that's not a problem. There are far larger machines out there, but we did do some work with the tuning of the out-of-the-box configuration. OpenStack is probably at risk of sinking under the weight of its own configurability, and to this end, actually, this is where the open infrastructure community comes into its own, because while we were doing 672 servers here, over at CERN, the team there have been managing 5,000 odd servers using the same technologies, and have developed a set of workflows and tools to enable it. So we actually, through the open infrastructure community, we've been working in close collaboration with teams like CERN, and that's testament to the approach of open infrastructure, that this kind of expertise and know-how is passed on and shared and then iterated on and improved and passed back again in this sort of reinforcing cycle. And CERN is by no means the biggest user in this case as well. The Verizon Media, I think, is the largest deployment following these kinds of methodologies, where they have 4 million CPU cores under management of a bare metal infrastructure tool like Ironic. I guess when you have that many systems, you start to come up to the analogies of the million-room hotel, in which one room is always on fire. And in large-scale monitoring, in large-scale infrastructure, we must similarly deploy large-scale monitoring in order to detect and weed out the failures that will be ongoing somewhere within a system of that scale. Cloud infrastructure I think, has learned some difficult lessons and has rolled with them in some ways, in that the infrastructure for a cloud environment is designed somewhat to be disposable, replaceable, and so they have the pets and cattle analogy, which fits very well there. But it only really works well as a principle if we are able to identify the failures before they start taking down the workloads on a repeatable level. And so the automation of the admin actions in order to service and put failing nodes into maintenance once they've been identified is key to maintaining a large-scale infrastructure with a high degree of service and reliability to it. The screenshot here is actually of a cloud-native tool called Prometheus, which is gathering data by communicating with the server BMCs on the compute nodes, and is extracting data from their system event logs. So we're seeing data about low voltage in this case, or other errors that are happening with specific servers within the environment, in order to enable us to identify the failures and to remove them quickly. So I think that's about all we have time to cover on this particular area. But I want to say that a couple of words on future plans for this kind of work. We're already applying the same principles to a machine which is twice as big again, so of the order of 1,300 compute nodes, and that machine is coming online this month. And I think similarly we will be evolving and iterating on the technologies in the open infrastructure environment and feeding those back as well. A couple of areas where that might be happening is very much more about sort of backfill on the flexibility. So the Cambridge system is very much focused in its present form on providing a large-scale Slurm partition, but there is an ever-increasing diversity in the requirements of platforms and the requirements of the hardware to be integrated within these heterogeneous environments. Also, it's going to be very interesting to bring about more of the capabilities of HPC into a Kubernetes environment. So adding platforms for managing RDMA fabrics and GPU resources, and offering those back as a service, as a managed service by the infrastructure teams in a way which makes the most of automation and integrates these highly performant tools into capabilities as well. One of the other areas that is very interesting and is developing well is the idea of providing a hybrid system, in this case, a combination of physical bare metal and some virtual compute resources with an optimized virtual service, either for performance or for capacity. And that's interesting because a combination of bare metal and virtualization brings about this sort of mix of flexibility where it is needed and performance where it is needed. And that really helps for target applications, these sort of multi-node complex applications where there could be a workload which is launched, but not from a commercial, a sort of a conventional command line link interface, but perhaps from a Jupyter notebook or from our Shiny environment or something, harnesses a high-performance compute resource and then brings data back for presentation and visualization, interactive refinement, and then again round the cycle again. So this approach, this presentation of HPC resources is something that we really see as being part of the vision of what you might grandly call the software-defined supercomputer. And that's very much the kind of resource that we are looking to provide, using cloud infrastructure and middleware and taking what we have at the moment in terms of HPC environments and adding this layer of rich sort of usability and flexibility to it without sacrificing the performance at the same time. So I think that's all I had time for. So I think I will stop there and say thank you very much to these people, in particular to John Garbett from our team and Paul Brown from Cambridge University, whose presentation I have largely plagiarized. Thank you very much.